Okay, come and just stand there and do act out the law of conservation of momentum.
States that in a closed system, a total linear momentum is conserved.
Lovely. Just under the law of conservation of momentum. V VF2. VF1. Lovely.
So, but I understand it, so even if I leave it out like I know.
And just swap that 2 and I and that there. Put the I first. Super. Thank you so much. Change in momentum is impulse. Who knows what the symbol for change of anything is? So let's do this, everybody. Change in momentum equals, what have we got here? Impulse. Let's just do that, everybody. Change in little p. See again, you guys are going with a big P. Little p equals impulse. Okay, I'm going to teach you something here because it just kind of fits in and it's going to be needed for the next question you're going to do, which is the one to finish off the last question, which was September, question 3, and you're going to need it for November 2018. The question I'm going to give you for homework today. Let's just have a look at impulse. Now, what did we say that changing anything is? Changing anything is final minus, so it's going to be P final minus P initial. Does that make sense to everybody? Yes. That is a change of momentum. Happy with that? Happy with that? Yes. It's also got another formula.
If net times change times if net times change time.
Lovely. Force times changing time. So force times changing time. Now that's a capital F, and that is also called impulse. A force acts over a period of time. It gives something momentum, or takes away momentum, it changes momentum, and its impulse is a force times time. Now there's another definition for impulse. Look at this here. What is the momentum final equal to? You've got it here. It's a mass times velocity final.
Yes, sir.
So there's another formula for change in momentum, and it's this. Delta P equals mass times change in velocity. What's changed? The mass hasn't changed, right? But a particular mass can change its velocity. The mass doesn't change, but its velocity changes, therefore the momentum changes. Does this formula here agree with you? Make sense? So this, you could also write it like this. Change of momentum is change of mv. But the mass stays the same, so it must be the v that changes. Because change of mv is change of p. Okay? Lovely. Now, seeing as I'm teaching, and we'll get back to your notes, but I was going to complete this. Does anybody know what it is when you divide something by time? It's got a certain term. Divide anything by time, and we have a physics term for it. It is called the... Anyone?
Time change.
Rate of change. So if we take change of momentum over change of time, we have something that is equal to rate of change of momentum. And all it takes is just go home, guys, and read it through. And then say to myself, what is rate of change of anything? It means, anybody? Divided by time, change of time. If impulse is equal to F delta T, so if delta P equals impulse equals F delta T, what else is it equal to? Mass times change of velocity. All of those are change of momentum. Is that a change of momentum? Force times a change of momentum? Mass times change of velocity is a change of momentum? Yes. All happy about that? So why don't we do this? Let's divide both sides by delta T. That cancels out. And what do I have? Mass times change of velocity over change of time. Who can tell me what I've got here? Anything divided by delta T is called? It's called rate of change of momentum. So the rate of change of momentum is equal to? Force. Do you see the math? Yep. I took two formulae for change of momentum of impulse. And then I divided both sides by delta T to get rid of it on this side. So rate of change of momentum is called force. Isn't that strange? I mean, think about that, physicists. Isn't that strange? Due from Newton, what do we do for Newton? What is Newton 2? Force equals mass times acceleration. Isn't a mass accelerating a change of momentum? So force, Newton 2, is rate of change of momentum is equal to mass times velocity. Have you done Newton 2? Yes. Because Newton 2, this is Newton 2, says that force equals mass times, acceleration. So therefore, that force, so that force and that force are the same. They are causing a change of acceleration, which is causing a change of momentum. So rate of change of momentum is also Newton 2, a mass being accelerated. Okay, you're going to have to think about it. But do you see the maths? Happy with that? Now we're going to need this formula to solve the last question of September question, which I gave you. Do you remember that last question? It was a car rides into something. And it had a crumple zone. Now, what is going to kill you if you ride into something with a car?
Inertia.
The inertia, good, or the rate of change of momentum. If you change your rate of change of momentum too fast, the g-forces, if they get above like 25 or 30, the g-forces it's going to kill you. That's what the same thing is going to crack an egg if we drop it. What? The rate of change is too fast for the egg. So that is going to be part of what you went and thought about. And what must we do? We must reduce the force. Do you agree with that? We must reduce the force of the egg as it comes. So can we change the momentum? No, it's going to start here. It's going to stop. That's a certain fix. We cannot change that. But what can we change on this side? Time. If we increase it, our force will become less. Because if you have a denominator that's big, that becomes small. If your numerator is big, which we can't change, your force would be big. We can't change that, but if we change the length of time that it takes the egg to stop, or change momentum, we can reduce the force to a livable accident.
So basically the time of the force has an inverse proportional.
Lovely. Exactly. Better than I could have said. The relationship between force and time is an inverse. You know, you're talking like a scientist. Well done. The force and time are inversely proportional, so to survive an accident, you need airbags, crumple zones, whatever can make that collision last longer will help reduce the force and therefore make it survivable. So now you know how to do that last question. For 3 marks, play around with the formulae, try and answer it for homework. And then, as I say, I'm going to give you the next question, which also involves change of momentum. But you're going to have to look at these. If you've got questions, you ask. Okay, let's just get a few more notes. Who else remembers stuff that we did last Friday? From total memory. What types of problems do we have? We have problems, let's act it out.
Elastic and inelastic.
We have elastic and inelastic. We have a formula called kinetic energy equals half mv squared. If the kinetic energy before equals the kinetic energy after, then it's a elastic collision. If they're not equal, then it's inelastic. Now, all of you did that problem well, but when you'd worked out your kinetic final and your kinetic initial, what you must do is you must then say why it's an inelastic or elastic collision. So if they're the same, you say Ki equals Kf, therefore it's elastic. But better, subtract Ki from Kf, so you get change of kinetic energy. Remember, a change of anything is final minus initial. Change of kinetic energy was not naught, therefore it's inelastic. So you guys, I know you can do equations and maths, wonderful. But do you know that question 3, every single one of you got that question wrong? Every one of you did it perfectly apart from one little thing.
So I said Ki is greater, so then Kf. So
Some of you guys did fantastically. I think there were a group of people who did say Ki is greater than Kf. Exactly. But what was the one thing that you guys got wrong that solved that problem? Okay, let's act it out. Watch this. I've got a Newton 1 weight. It's going positively. Just act it out, everybody. So it's got a mass times a positive velocity, right? Hits another rugby player who's going head on, which is south. The first player was going north, which we said was the positive. But the guy who was coming against him was south. Let's act it out. So this guy's positive, this guy's negative. What did you forget in that problem? The direction for player number B or 2 must be negative. How? And 18 out of 18 forgot about that. So when we do this, it means your V must be negative. And let's see how easy it is to correct that. But what you must do is you must go and redo the part of that problem, which is the whole bit that you got wrong, plus by luck the kinetic energy parts of it were right, because half mv squared didn't matter if V was positive or negative. Do you see what I mean? So by luck, you must also redo that V, that kinetic energy part, because you're going to get a different velocity if you take it, that the rugby player number 2 is negative. So you're going to get a different velocity, and then you must solve that problem correctly, including the kinetic energy. So guys, all I ask is that you will go and do it. Correct your homework. We are not going to settle for wrong. We must get it 100% because otherwise it was 100%.